Friends, this is Mr. Tomski speaking to you from the great beyond. Well, actually, I'm beyond Milwaukee County. I am in Oshkosh on my retreat, and the sub is playing this video for you. So we're going to do the notes from lesson 10.1, lines and segments that intersect circles. You should have those notes in front of you, and you should be filling them in as we go along. So here we go. Let's start off by defining a circle. A circle is the set of all points that are equidistant from a given point called the center of the circle. I'm pausing. It is the set of all points that are equidistant from a given point called the center of the circle. And I'm going to give you just a few seconds to write that down. And notice that I have drawn a circle. I put a point in the center and I labeled it D. And so our notation is going to be a little circle with a D, like I'm showing here to the right, and we're just going to call that circle D. Now the next part of the notes, we just define a lot of things. And there are some places for you to fill in, but you're going to be able to write this quickly because there's only a word here and a word there. So let's start off by defining a segment whose endpoints are the center and any point on the circle, and that's a radius. And mine's in color, yours is not. And you can see that the red is the radius. Now a chord is a segment whose endpoints are on a circle. So you can see that we have a green chord up there. And I'm going over it now with the cursor. A diameter is a chord that also contains the center of the circle. So you see the diameter right there going through the center of the circle. Now I will tell you right now, great test questions. A chord is always, never, sometimes a diameter. And it's sometimes. This chord is, this chord up top is not. This chord that goes through the center is. Turn it around. A diameter is always, never, sometimes. A chord, always. All right, let's continue on. And a secant is a line that intersects a circle in 2 points. And I'm now here at this bottom circle, and here's the secant intersecting the circle in 2 points. Whereas a tangent is a line in the plane of a circle that intersects the circle in exactly 1 point. Right there, point B. And that's called the point of tangency. Point of tangency. Now the tangent ray AB or the tangent segment, segment AB, they're also called tangents. So a tangent can be a line, a segment, a ray. It doesn't matter. You can see that I've shifted the notes down for these examples 5 through 10. And I am going to give you a few seconds. I'm going to pause. I'm going to put my answers on, and then I will restart my video. So right now, you should be answering 5 through 10. Alrighty. So you can see that I have named the circle Circle C. 2 radii, those are segments from the center to the end of the circle. So your answers are segment CA and segment CD. 2 chords. Now they have to be segments hitting the end of the circle. So it's segment HB and segment AD. One of those is a diameter, one of those is not. So number 8, segment AD is a diameter. A secant intersects the circle in 2 points. Now I could have called this line HB, but I used the outside points and I called it line GK. Now a little note on notation. Remember, when we don't put the arrows, we mean line segment that stops at those endpoints. And when we include the arrows, we mean the line goes on forever and ever. And then finally, a tangent and the point of tangency, line GE is tangent, and the point of tangency is point F. And we're ready to flip the page over. All right, on page 2, problem 13 there says, tell how many common tangents the circles have and draw them. Well, common tangent is using the word common, meaning they have tangents that they share. So, how many do these have? Well, a ruler helps. I'm going to take a ruler here, and it looks like I'd be able to somehow draw a line up top that's common to both. And it looks like I'd be able to draw one down below that's common to both. So our answer is that these two circles, why don't I give them some letters, circle A and circle B, are going to have two common tangents. I'm going to pause the video and draw mine, you draw yours, and then I'll continue. Alrighty, so your picture should look a little something like I've got drawn there, with your two common tangents of circle A and circle B. Now, for number 20, the next example, it gives you a triangle there going from the center of circle C to point B, and it gives you some lengths, 9, 15, and 18, and it says, hey, tell whether that segment AB, and I'll put the little segment sign above that, is tangent to circle C. Explain your reasoning. And if your reasoning is, yeah, it's tangent because it kind of looks tangent, that is no good. Remember that we don't go by looks, we go by theorems, formulas, equations, and so you're like, yeah, well, what do I have? Well, you have nothing yet. But if you scroll down a little bit, and I move the paper down a little bit, we have a theorem right below that. So I actually put the problem in front of the theorem and make you think a little bit. We've got a theorem called the tangent line to the circle theorem. And it says, in a plane, a line is tangent to a circle if and only if the line is perpendicular to the radius of the circle at the endpoint of the circle. So in the picture here to the right, line M is tangent to circle Q if and only if line M is perpendicular to the radius segment QP. And they show us the right angle there, so in that example it is. But back to the example above, you tell me, is segment AB tangent to the circle? I'm going to pause, I'm going to do a little math, and then turn it back on with the solution. Alrighty, so if that was perpendicular, a right angle would be formed, and the triangle ABC, would satisfy the Pythagorean theorem. So we check out whether 9 squared plus 15 squared equals 18 squared. 81 plus 25, does that equal 324? 306 does not equal 324. So segment AB is not tangent to circle C. It's close, but not tangent. All right, so our next example is we are told that point B is a point of tangency, and we're asked to find the radius of circle C. And so I am going to ask your sub to pause the video for a second and give you a minute or so to see if you can tell us what the value of the radius R is. Okie dokie. So we set up the Pythagorean theorem with triangle ABC. We say r squared plus 14 squared. The hypotenuse, segment AC, is r plus 7, so we have to square that. And if any of you squared r plus 7 and said r squared plus 49, oh, you'd be killing me. We got to remember that we have to FOIL r plus 7 times r plus 7. And I'll get my hand out of the way. That's r squared plus 14r plus 49. Lucky for us, the r squareds drop out. And hold on. Thank goodness for the pause button. And I had done that problem wrong. I don't know why I was taking a square root, what I was thinking. Anyway, the r squareds drop out, and we get 14r equals 207. Divide both sides by 14, which I'm showing here real quickly, and r is 14.8. All right, I'm going to bring this baby home with what's on the third page of your notes, so turn it over. All right, we're on page 3, and we're given a circle, circle C, and we're told that points B and D are points of tangency, and we're given segment AB is 2x squared plus 4, segment AD is 22, and we're said, hey, find x. Well, it would be nice if we had a way to find x. I mean, we don't have an equation. We could set 2x squared plus 4 equal to 22, but why could we do that? Well, once again, I kind of put the cart before the horse, so to speak. I put the problem before the theorem, but here's the theorem. The external tangent congruence theorem that says tangent segments from a common external endpoint are congruent. So if you look at the picture here on the right, SR is congruent to ST if they're both tangent. And back to our problem up above, AB is congruent to AD because we're told that B and D are points of tangency. So I'm going to pause it, and your sub will pause it, solve for x, and I'll give you my answer in a second. And so 2x squared plus 4 equals 22. Subtract 4 from both sides. 2x squared equals 18. Divide both sides by 2, so that x squared equals 9. Take the square root, get x equals 3. And by the way, when we solve second degree equations and we take square roots, we normally concern ourselves with plus or minus square roots unless we have a physical reason to ignore the negative root, and the length of a radius of a circle or the lengths of sides, they can't be negative. So for the most part in this geometry unit in chapter 10, we'll be ignoring the negative roots. All right. So that is lesson 10-1, and the sub will pass out the homework 10-1, and that will be due I should say, on Monday. But since the video is taking about 13 minutes, you ought to have a lot of time to get most of that done. Have a nice weekend, Cavaliers. I will see you on Monday.